All right, welcome back, folks. So up to this point, we've been working on the one-way ANOVA, where we only had one independent variable, but it had multiple levels to it, more than two. So remember with the t-test where we were comparing only two groups, the ANOVA allowed us to compare three or more groups, but only on one factor so far. At this point, we're going to be moving into some more complex designs that allow us to have multiple independent variables. In this class in particular, we'll stick to just two independent variables, but you could have three or even four. Technically, you could have any number, but beyond four, it starts to get pretty unwieldy. But in this class, we'll focus on two independent variables at a time using a design called the Factorial ANOVA. So before we get too far, we have to establish some terminology, some definitions. Factors are our independent variables, and levels are the number of conditions for each IV, for each independent variable. So for example, if we had an experiment, we were looking at the effects of drug A versus drug B on anxiety, we would have two factors, and each drug might have different levels, right? So for drug A, you might randomly assign people to either take 10 milligrams versus 20 milligrams versus 30 milligrams, so three conditions. And likewise, drug B might have four levels, so 5 milligrams versus 10 milligrams, 15 and 20 milligrams. So with a factorial design, every factor is paired with every other factor. It's fully crossed, so all combinations are included. So if we look at the table, we would have participants in each one of these cells, right? So we would have, in this case, 12 different cells here corresponding to each participant got some level of drug B, and they also got some level of drug A. We would call this a 3x4 factorial design. So the numbers represent the number of levels that we have, and we know that it's a two-factor design because it's 3x4. If it were a three-factor design, it would be 3x4x2 or something. There would be more by statements there. So the 3x4 indicates that you have a factor with three levels, fully crossed with a factor with four levels. We, at this point, are featuring, are looking at between subjects factorial designs, which means you have different participants in each cell. So in this case, you only would receive one level of drug A, and you'd only receive one level of drug B. In the next lecture, we'll get into within subjects designs, where the same people will receive multiple levels of the independent variable. For now, purely between subjects, so different subjects in each cell. Why are why factorial designs are so cool is they allow us to test for interactions. So an interaction is a situation where the effect of one independent variable on the dependent variable depends on the level of another independent variable. So there's some terminology in here that we just have to get straight. We have to kind of memorize, and interaction is definitely one of them. So we have to understand what an interaction is. The effect of one independent variable depends on the level of another independent variable. And we'll see what that means more clearly in the upcoming slides. So let's simplify our drug example. So what type of design is this? I hope you said a 2x2 factorial design, because drug A has two levels, drug B has two levels, so it's 2x2. They're fully crossed, so it's a 2x2 factorial design. And let's put some numbers in there to represent anxiety scores. In this case, there's no interaction. And I think that's a little bit hard to see in the table, so let's plot these values. What we see here is we have the effect of drug B down on the x-axis, and whether or not people received 10 or 20 milligrams of drug A is represented by either the solid or the dashed line. And what we can see here is that these lines are parallel. So if we look at the effect of drug B on anxiety, as the dose increases in drug B from 5 to 10 milligrams, the anxiety symptoms for people who took the low amount of drug A, 10 milligrams, reduced by 4. Likewise, as we increase from 5 to 10 milligrams on drug B, the effect of anxiety, or the effect of drug B on anxiety reduced from 5 to 1, a change of 4. So the change is the same regardless of what level of drug A we took. So the effect of drug B on anxiety did not depend on the level of drug A that we took. So there is no interaction here. We can see that because these lines are parallel. The effect of drug B on anxiety does not depend on the level of drug A. And we looking at that the opposite way too. We can see that folks who took a low amount of drug A, the dashed line, on average experience more anxiety, right, on average, than folks who took the high amount of drug A. That difference was 5. On average, people who took low amounts of drug A, 10 milligrams, experienced 5 more symptoms of anxiety than people who took the high amount of drug A, 20 milligrams. But that change didn't depend on whether or not we took a low dose of drug B, 5 milligrams, or we took a high dose of drug B, 10 milligrams. The effect of A on anxiety was the same across levels of drug B. So there is no interaction here. So let's consider an effect or an example where there is an interaction. So again, here's the table of values. I find it easier though to interpret the figure. Here we can see these lines are not parallel. If I extended them out, to a certain point, they would eventually intersect somewhere out here. The lines are not parallel with each other. And we can see that the effect of drug B on anxiety depends on the level of drug A that we took. If we took a low amount of drug A, 10 milligrams, drug B has no effect on anxiety. It doesn't matter if I took a low or a high dose of drug B, my anxiety remained the same. But if I took a high dose of drug A, then drug B reduced anxiety. We see that the effect of drug B on anxiety depends on the level of drug A. And we can flip it around the other way too. We can see that on average, people who took a low amount of drug A had more anxiety than people who took a high amount of drug A, but that this effect was less pronounced if you took a low amount of drug B versus if you took a high amount of drug B. So the effect of one independent variable depended on the level of the other independent variable. So when I say the effect of an independent variable, I mean the change that we see as we change from one condition to another depends on which condition I am for the other independent variable. So let's work through an example from start to finish. Here's one from my own research. This is based on a paper I published a few years ago. I simplified it a lot to make the numbers easier to work with and whatnot, but this is a basic story that we told in the paper that we published. We were studying self-efficacy, where self-efficacy is one's confidence that he or she can perform some task. So if you have high self-efficacy, you're pretty confident. If you have high self-efficacy for this course, you're pretty confident you're going to do well. If you have low self-efficacy, you're not as confident that you will be able to do well. So most of the past research through the 80s and 90s showed that self-efficacy was positively related to the effort that you put forward. So if you're more confident, you put forth more effort. In the 2000s, research started coming out showing that, well, actually sometimes self-efficacy is negatively related to effort. So Sometimes you get a positive effect, more self-efficacy, more effort. Sometimes you get a negative effect, more self-efficacy, less effort. And so our hypothesis was that this relationship would depend on the amount of time that was available, such that when you had a lot of time available, the more confident you were like, well, okay, I can do this. I have time. I'm confident. I'm going to put more effort in and get this task done. Whereas if you were very limited on time and you were very confident, then you would reduce the amount of effort. Think about yourself studying for an exam. If you have multiple exams and you have a lot coming up and you have a lot to study for, do you put your time and effort into the one that you're very confident you're going to succeed, or do you put it into the exam that you're less confident? Probably you put it into the less confident exam, because the one for which you're already confident, you don't need to study. You already think you're going to do well. So we thought there would be an interaction between self-efficacy and time available. So what we did was we randomly assigned participants. Again, I kind of fudged these numbers to make it simple. I just said there was 40 participants. Our study was a little bit more complex than this, but this is the simplified version, right? So for our purposes here, we randomly assigned participants to one of 4 conditions. It's a 2x2 factorial design where self-efficacy can take on high or low values. So in the low condition, what we had is we had everyone do a task that was ambiguous to them. It was a new task. I think it was a stock prediction task, and it was just a game we made up, basically. So we had them do a practice trial, and then we gave them some feedback. But the feedback was false, right? So we either gave them feedback telling them that they did very well, so that was the high self-efficacy condition, or we gave them feedback telling them that they did very poorly, and that was the low self-efficacy condition. After that, we had them do another trial. So going into the subsequent trial, you either had just gotten feedback that you were good at this task, or you had just gotten feedback that you're bad at this task. We also manipulated the time that they had to complete the subsequent trial. So either they had an unlimited amount of time, and so they could take as long as they wanted, or we put a very strict time limit on the amount of time that they had available to complete the task. And then our dependent variable was just the amount of effort that they put into the stock prediction task. I think we operationalized that as the number of attempts that they made to solve the problems. For our purposes here, we can just say we measured effort in some way. So I have our data here for each of our 40 participants, and they are split into 4 cells according to low versus high self-efficacy, split with either an untimed or a timed condition. As before, we need to organize our results into a source table, except now our source table has a few more rows to it. Whereas before we just had group, right? The variable that we manipulated, which group were you in? If it was plants listening to music, it was rock, classical, rap, control, something like that. But here we have 2 groups now, right? We have self-efficacy, low and high, and we also have time available. So self-efficacy is SE here, and time available, TA, time available, low and high. And then we also have the intersection of those, the interaction. So that's the SE times time available cell. Like before, then we also have error and total. So what do I like to do first? The simplest part to fill in is our degrees of freedom. Our group degrees of freedom is the same as before. It's K minus 1. So however many levels you have in each group, it's that minus 1. And then the interaction is just the product of those. You can just multiply them together. Our error term is our DF total, our degrees of freedom total, subtracting out the group and interaction terms. Or another way to do that is it's the total N, the total number of participants, ignoring, it doesn't matter what group they're in, just the total number of participants minus the number of cells. So in this case, it's a 2x2 factorial design, so we have 4 cells, right? 2 crossed by 2. And again, our total degrees of freedom is our uppercase N minus 1, where uppercase N is our total number of people in the experiment. So self-efficacy had 2 levels. So K minus 1, 2 minus 1 is 1. Time available had 2 levels. K minus 1 is 1. The interaction is just the product of these. So 1 times 1 is 1. our total degrees of freedom is our total number of people minus 1. So remember, we had 40 people total, so 39. And then our error is just we can subtract our group and interaction degrees of freedom from our total degrees of freedom to get that n. Alternatively, we had 40 people total and 4 cells, so that also gets us to 36. As shown on the slide here, the next thing we would do is compute the sums of squares total. And I don't go into it here because, again, we've done it many times. So this is just ignoring all the conditions, just looking at each individual person and subtracting their score from the grand mean. So subtracting their score, x, the amount of effort they put in, from the grand mean, squaring that result, and taking the sum. And when we do that here, we get 35,263.10. You're encouraged to go and do that for yourself if that's unclear, but for now I'm going to say we've done it multiple times now, so we'll just move forward. Next, we need to do the sums of squares group, where this is the same as the one-way ANOVA that we did before. We have the group mean, so x bar j, minus the grand mean, just x bar, square that result, multiply it by the number of people in that group, right? It's a lowercase n, and then take the sum. The only thing here is we have to be careful not to get confused because now we have two groups, self-efficacy and timed versus untimed. So first we're going to do the sums of squares for self-efficacy. So we need the means for low self-efficacy, which here I've highlighted. I'm just ignoring the timed versus untimed. It doesn't matter. What matters is that all these people are in the low self-efficacy condition, and the mean of that column is 152.25. Likewise, all the people in the high self-efficacy condition are highlighted here, and that mean is 151.05. So to compute my sums of squares group, I can simply subtract each mean. So I have my low self-efficacy mean, 152.25, minus the grand mean, 151.65, squared, times how many people are in the self-efficacy, the low self-efficacy condition. Well, 20, right? There's 10 in this cell, 10 in this cell, 20 total in this column. And doing that, I get 7.2. I can do the same thing for the high condition, and it comes out the same as 7.2. Be careful there, that's a special condition. It won't always be exactly the same. It just worked out that way this time, and it's a function of it being a 2 by 2. So it just happens to be the same here, but that won't always be the case. You actually need to compute each level. And then it's the sum of squares, so we can just add them together. And we get 14.4, and we can plot that in our table. Moving along, we can do the same thing with the untimed condition, right? We have our untimed mean, which is now I'm just ignoring across self-efficacy. It doesn't matter what self-efficacy condition you're in. All of these people, highlighted in yellow, are in the untimed condition, and their mean is 168.05. Likewise, the mean for the timed condition is 135.25. Again, I can apply my equation by subtracting each group mean from the grand mean, squaring the result, multiplying by the number of people, and then summing those together. So for the low, I have a mean of 168.05. I subtract out the grand mean of 1.51.65, square that result, multiply by 20 because there are 20 people in the, I'm doing the untimed condition. And the result I get is 5,379.2. I can do the same thing with the untimed condition. And again, these numbers are the same. That's just a special case. It's only because we're doing a 2 by 2. That won't always be the same, so you actually have to compute each of these. So don't be confused by that. It's just how this one happens to turn out. Adding them together, I get 10,758.4, which I can then go and pop into my source table. Next, we'll want to do our sums of squares for the interaction term. To do this, we have to do, there's an extra step here. We have to compute our sums of squares cells. Now don't get confused. the sums of squares cells is a step along the way to computing the interaction term sums of squares, but they're not the same thing. So let's work through it. The sums of squares cells is computed the same way as we did our group sums of squares, except now we're only looking at one cell at a time. So our low self-efficacy untimed cell, that's just one cell here, is the mean of all the people in that cell. Likewise, for the high self-efficacy untimed, the low self-efficacy timed, and the high self-efficacy timed. So I've just computed the means of each cell. And then I do the same process that I did before. I'm subtracting each cell mean from the grand mean. So here I have 154 minus 151.65 squared times how many people are in the cell? 10, only 10 people per cell. And I do that for each of these combinations and take the sum. So the same process as before. And that's my sums of squares cells. But recall that that is not my interaction term. There's another step here. The sums of squares cells contains information about sums of squares of the two main effects, which I realize I haven't introduced main effects yet, but we'll talk about that in a few slides. But the two groups by themselves, sums of squares self-efficacy and sums of squares time available, that information is contained within sums of squares cells. So we need to subtract it. So the interaction term is sums of squares cells minus those other sums of squares. So the sums of squares for self-efficacy and the sums of squares for time available. And we get the result there of 8,584.9. Like before, our error term is just our total minus everything else, right? Our total is total. It's all we have. And so what's left over after we compute all the other sums of squares is the error term. Like before, to compute our mean sums of squares column, we simply just divide across. So 14.4 divided by 1 is 14.4, and these three are all easy. We're dividing by 1 in this case. Here we have 15,905.4 divided by 36, which is 441. And then our F column is computed the same way, except be careful here because you're always using the same error mean square. It's always the error mean square, a mean squared error in the denominator. So the F for self-efficacy is 14.4 divided by 441.82. The F for time available is 10,758.4 divided by 441.82. And for the interaction term, it's 8,584.9 divided by 441.82. So we're always dividing by our mean squared error. We just divide each one by our mean squared error to find our F's. Here I've given some stars to tell you that I've looked this up and see that this is non-significant, which we know that because it's less than 1. Remember, F is a ratio of how much variance there is between groups versus within. So this means there's more within group variance than there is between. So we know that this is non-significant, but nonetheless, we could look it up. And our time available and our interaction effect are both significant, which I've just indicated with some stars here. So we could look them up in the F table the same way that we did before. Important to note that our mean squared error is the average of our cell variances, and in fact, it's the weighted average of our cell variances. So just like before, we have the assumption of homogeneity of variance, and thus when we go to do our post hoc tests, we're going to be able to use this value as our estimate of population variance. Right? That's going to be useful to us because then we can use our degrees of freedom from the same, from the error part of the table. So I mentioned main effects on the other slide, and I said I'd come to them eventually here. So here's another piece of vocab that we have to just kind of get locked cold. We have to really understand the difference between main effects and simple effects. Main effect is the effect of one of the IVs averaged across levels of the other IV. And a simple effect is the effect of one of the IVs at a level of the other IV. So here, what's in our omnibus table, and here I've just shown the last column, just the F column, is our main effects. That's what's in the omnibus table, the main effects. And so our main effect of self-efficacy is the effect of self-efficacy on effort, our dependent variable, averaged across levels of time available. So if we look at that here and we took, well, the averaged across is the middle of these two lines, wherever the middle of the dashed line and the solid line are. So here, the average is kind of right here, right? And if I come out to the high, the average is right here. So if you imagine the line that my cursor is tracing here, you can see that on average, there's no effect of self-efficacy on effort. On average, averaging across, there's no main effect. But does that mean that there's no effect at all of self-efficacy on effort? No, I think that this plot shows very clearly that, well, it depends. When time available is untimed, when you have unlimited time available to you, there seems to be this positive effect of self-efficacy. As self-efficacy increases from low to high, this line is increasing effort. That's a simple effect because I'm looking at the effect of self-efficacy at the untimed level. I'm looking at the effect of self-efficacy within one level of my timed versus untimed variable. Likewise, if I look at the timed level, the solid line, there's this negative effect. So sometimes you'll hear that main effects are qualified by the presence of an interaction. And the word qualified there is used in the sense of like when you say something like, well, let me qualify what I just said. You know, it's saying, well, there's no main effect, but let me qualify that. It's because in this case, there are offsetting simple effects. One goes up, the other goes down. On average, no main effect. So the effect of self-efficacy on average across levels of time versus untime is nothing. There is no effect. Okay, there is a main effect of time available. That would be the average of this line here, the average of this dotted line, which is somewhere around here, right? Compared to the average of this solid line, which is somewhere around here in the middle. And if we look, yeah, there's a gap there. So there is a main effect of time available on effort. Again, that main effect is qualified by the presence of an interaction. Because if we come at the low self-efficacy level, we can see that there's hardly any difference here. Instead, it's being driven by the high self-efficacy condition where there's a big gap here. So whenever we see an interaction, we have to be sort of careful about interpreting our main effects. They are qualified. So really we need to plot and then probe our interactions. So by probe, I mean when you have a significant interaction, kind of similar to before when we had a significant omnibus test, it told us that one of these means was different from one of the others. Well, when we have a significant interaction, it means that one of these effects, it means that there's lots of different combinations of ways that we can have an interaction. It means that the effect of one independent variable on the dependent variable depends on the level of the other, but we don't know what that looks like. So let's consider some examples. So if I have my independent variable down here, I have my dependent variable here, and I have an interaction, I might have an interaction that looks like this. Let's see. I'm going to make this dashed. Oh, sure, we'll just do it this way. I might have an interaction that looks like this, right, where they cross over. Those lines are not parallel. But I might have something that looks like this. Those lines are not parallel. Or I might have something that looks, whoops, like this. Those lines are not parallel. As you see, lots of different ways that an interaction can play out. So just finding in an omnibus table that we have an interaction doesn't tell us anything. Well, it tells us something. It tells us that the effect of one independent variable depends on the level of the other independent variable. But it really doesn't tell us anything more than that. Instead, we need to go forward and probe. We need to plot that interaction and then see if each of those lines is significant. Like this looks like there's a significant effect here for this solid line, but is this dashed line significant? Hard to say. Maybe, maybe not. Is this gap down here between them significant? It doesn't look like it, but maybe, I don't know. Is this up here? Yeah, it looks like it is. So the same way with a one-way ANOVA, we can't just look at the plot and say, well, this looks significant, this looks... No, we have to do tests. We have to do significance tests because just because two values are not the same on the surface, as we know, there's sampling error. They could just be different because of sampling error, just random chance. Likewise, with the interaction, you might find data that looks like this. Okay, I mean, those lines are not perfectly parallel to each other, right? They will eventually intersect out here, but they look pretty parallel. That's why we need the interaction test, because the lines will never be perfectly parallel, right? There's always going to be some sampling error. The interaction test tells us if that deviation from parallel is significant or not. All right, so there's a few ways that we can test interaction terms. We're going to start with doing simple effects, right? And this is going to be the most general way and the way that we would use if we had more than 3 levels of the IV. In this case, since we have a 2x2, it's sort of a special case, and we could get away with not doing this. We're going to run through it anyway because once we have more than 2 levels of each independent variable, we will need to do this. In the second example I present, that will be the case. So here I have my plot, and I have my means for each of those points here, the high, high, low, 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 high, high, low, right? And I can put them in a table. And what I need to compute here is what are called marginal means. So this 168.05 is the mean of untimed across self-efficacy. It's the average of these two values. Likewise, 135 is the average across self-efficacy for the timed condition. I can do the same thing for low self-efficacy across timed and untimed, and high self-efficacy across timed and untimed. So if I want to test simple effects, right, what I'm looking at is right now I'm doing the effect of self-efficacy at untimed. Going back to my figure, the effect of self-efficacy at untimed. So I'm only looking at this dashed line. That's important. Simple effects is the effect of one independent variable at a level of the other one. So when I'm testing self-efficacy at untimed, I can get rid of the timed portion. I don't need it right now. I'm not dealing with that right now. And instead, what I'm doing is sort of just a one-way ANOVA here. It's the same as the first part of a one-way ANOVA. So since my timed condition doesn't exist for me at the moment, my grand mean is really my marginal mean for my untimed condition. So I can do my sums of squares. I compute the difference between my low self-efficacy condition and my grand mean, which is in this case my marginal mean. Square that times how many people are in that cell, 10. I do the same thing over here, 182.1 minus 168.05 times 10 people. Oh, sorry, square it and then times 10 people and take the sum. I do the same thing at the timed condition, right? I take 150.5 minus 135.25 and square it times 10. 120 minus 135.25, square it times 10 and take the sum. And I can put those into a source table here. Same way, what did I just compute was my sums of squares. They had 1 degree of freedom because in each case there were 2 levels of self-efficacy, k minus 1. So I can compute my mean squares. But what's important, oh, I guess I skipped something there. What's important is look at my error term. This should look familiar. This part's not as important to us, but where did I pull my degrees of freedom and my mean squares from? Directly from the omnibus table. So in some ways, it's like doing a one-way ANOVA, right? Just ignoring the other condition, but only the first part, only the sums of squares part. When I compute the error term, I'm using all the data, not just half of the data, all of the data. Can you do that somewhere else? No? All right. So I can use my mean squared error from my omnibus test and the degrees of freedom. I've worked backwards and solved for the sums of squares, but we don't really need that. We're not going to use that because all we really need is this mean squared error and the degrees of freedom. So I divide my mean square for self-efficacy at untimed by my mean squared error to get my F. In this case, it's significant. And my self-efficacy at timed divided by my mean squared error, and that's also significant. We could also use t-tests here, right? We could compare means and use our mean squared error as our estimate to probe this interaction. So for example, if I wanted to test the effect of timed versus untimed at low self-efficacy, I think it helps to look at the figure. Oops. So I'm looking at this comparison here, timed versus low timed at low self-efficacy. Is that little tiny gap there significant? I could do it with sums of squares. I could also, in this case, do it with t-test, right? Because I'm only comparing 2 means. And in this case, it's 154 minus 150. That's the difference at that low end. And in my denominator, I'm using my mean squared error as my estimate of population variance. And in this case, we find that no, that's non-significant. That little tiny gap there we saw is effectively 0. And the fact that they're not exactly the same, that 154 and 150.5 are not exactly the same, is just sampling error. I can do the same thing at the high end. And in this case, I do find a significant effect. I find a T of 6.61 with how many degrees of freedom? 36, right? Because I'm using my mean squared error as my estimate of population variance. And that is this test out here. So that is significant. I could also use a Tukey, right? Where, recall I'm using the studentized range statistic to use Tukey, so I need to put my means in order. So in this case, the first position is the high self-efficacy timed condition. That's the lowest mean, 120. The next is low self-efficacy timed. That's 150.5. Low self-efficacy untimed and high self-efficacy untimed. I can find my R for this case, it's Tukey, so it's always the same. So it's the largest position minus the smallest position. So 4 minus 1 plus 1 is 4. Or it's just the number of groups, 4. We could do the same thing with Newman-Cool's. I won't walk us through it, where we would compute a different R for each comparison we sought to make. So what is Q critical? Based on our R, our alpha, and our degrees of freedom, our alpha is always 0.5. In this case, our 0.05, excuse me. Our R is 4, as we just found. And our degrees of freedom, again, 36, taken from that omnibus test, because we are using our mean squared error as our estimate of population variance. Coming to my table, I have a range, an R of 4, 36 degrees of freedom, no 36 in my table, so I go down to the next nearest number, which is 30, and I find my Q critical is 3.85. Plugging that in, I can plug in my mean squared error. I can plug in my sample size, which in this case refers to each cell, each mean that I'm comparing, so that's 10. And by doing some cross multiplying, I can find that my honest significant difference is 25.59. So the difference between these two is only 3.5, so that's not significant. 3.5 is less than 25.59, my critical value, so that's not significant. The difference here is 62.1. So because that is greater than my honest significant difference, we do have a statistically significant result. And I can compare the other ones as well. If I want to do, so moving along quick, we will go through another example in which we go through simple effects again. Experience teaches me that it takes at least 2 examples to get it. So if you're like what's going on? Don't worry about it. That's okay. We're going to go through another example that's not a 2x2. We're going to go through a 2x3 example, and that will hopefully solidify some of those simple effects analyses for you. Before doing that, talk quickly about how we would run these analyses in SPSS, similar to how we set up our analysis before, where you have to have your independent variables as variables in SPSS, and then your dependent variable next to it. Except now we have 2 independent variables. So in this case, in this example, they had a factor called age, which was just young and old, which they coded 1 and 2. And they had a factor called condition, which had values of 1, 2, and 3. 1, 2, 3, 4, 5. 5 conditions up here. And then they had their dependent variable in the next column. In this case, it was recall. So to run the Factorial ANOVA, we're no longer in compare means. Instead, we come to analyze, and we come to our general linear model. And this is a univariate general linear model. We can add in our variables. Our dependent was recall, and our fixed effects. Those are our independent variables, were age and condition. And here I've just asked for some options and said, give me the effect size here. So I clicked the options button, and I requested some descriptives and some effect sizes. We can see that the table is largely the same as what we had before. We have some extra stuff in here, the corrected model intercept. We won't do much with that. We don't need that. But what we're looking down here is here. We have an effect for age, an effect for condition, an interaction term, and an error term, and a total term. So again, corrected total, we don't need that. But from here to here, it's all the same, right? We have sum squares, degrees of freedom, mean square, F, and significance. Remember, a significance of 0.000 does not mean P equals 0.000. It means P is less than 0.001. Remember that P can never actually equal 0. So SPSS is just rounding here. So be careful how you report that. They also report the effect size, and what they're reporting here is a partial eta squared. So up to this point, we've talked about eta squared, but we haven't talked about partial eta squared. And the reason is, for the one-way ANOVA, there's no difference. partial eta squared equals eta squared. For more complex models, they're different. Recall that our eta squared is just our sums of squares effect over our sums of squares total. Our partial eta squared is only the effect that we're interested in plus the error. So it doesn't include the sums of squares from the other factors, right? With a one-way ANOVA, we only had one factor, so it didn't matter. Here we have multiple factors. We have the main effect for one variable, the main effect for the other, and the interaction term. If we put all those sums of squares in the denominator, it makes our denominator larger, and it makes our partial eta squares smaller. Or sorry, our eta squared smaller. So eta squared will always be smaller than partial eta squared. They're both interpreted the same way, though the proportion of variance accounted for. Partial eta squared is sometimes preferred because it isolates the variance for just that one factor. Regardless, it's important to just know the difference between them and to report correctly. So if you're reporting a partial eta squared, don't report it as an eta squared because remember, partial eta squareds will always be bigger, so that will be slightly misleading. But we interpret them the same way. It's the proportion of variance accounted for in our DV by this variable. So, after everything we went through, how would you write this up? I'll leave that to you, right? You have to think about, well, you have to make a claim. What did you find? You have to support that claim with evidence. What is the evidence that you would use? Well, you have an F with degrees of freedom. In this case, you have a couple of Fs, right? You have a main effect, another main effect, and an interaction effect. You have the eta squared that is associated with each of those effects. Remember to always report your error terms, your mean squared error, your p-values, or at least p less than 0.05. And then you might write up your simple effects too. We'll talk more about this as we go on and as we complete homework number 2. But take a shot at it yourself. Start getting comfortable with, okay, I make a claim. What is the evidence I need to support that claim? And what's the most logical way to present these data? We're getting to a place where actually it might make more sense to make a table and then have some statements describing the table because you have so many results. Like I said, we can talk about that later as we prepare homework number 2. You'll get some practice. That's it for this one. We're gonna go ahead and do another part 2 where I do the second example in order to keep these videos to a reasonable length. See you soon.